Hello, this is Mr. Hupp, and real quickly I want to do a physics review for this project because some of the things we need to do are going to call in some things that we've already done, but you've probably forgotten. So let's take a look at that. So we're going to look at some assumptions. For these experiments, we are assuming that the devices reach terminal velocity instantly. Therefore, the velocity and final velocity terminal velocity and final velocity are exactly the same. We know it's not true. We know that there is some acceleration at the start before it reaches terminal velocity, but to keep things simple, we're just going to assume that the average speed on the way down is the terminal velocity, and that is also the final velocity. We're also going to assume standard pressure and temperature. This will simplify our calculations, so we don't have to think about it. And we are assuming that an impact velocity of less than 2 meters per second is safe for your cargo. So your target is to get below 2 meters per second. So you're going to drop your device from some height. This is going to be a y displacement. Think about the xy axis. You need to determine the terminal velocity using this formula. The y displacement divided by time is equal to your terminal velocity. Velocity is in meters per second, displacement is in meters, and time is in seconds. Be sure to convert all of your measurements to a common unit. At terminal velocity, the weight is equal and opposite to the drag force. So that means the weight is equal to the drag. Because it's not speeding up, it's at constant velocity. It's not speeding up, it's not slowing down. So the weight is going to be equal to the drag. That means the force of gravity is equal to the drag force, which is going to be the mass times gravity. And mass has to be measured in kilograms. Gravity is meters per second squared, and it's 9.81 meters per second squared. That's what we're going to use for these calculations. Force will be measured in newtons. This is the coefficient of drag formula. Remember that the coefficient of drag is a ratio, so it has no units, and that D stands for drag. It's also the force of drag, and it's measured in newtons. A is for area in square meters, and we'll talk more about that in just a moment. Rho is density, and that's kilograms over cubic meters, and it's the Greek letter rho. It's not a letter P. And V stands for velocity in meters per second. You will be calculating the coefficient of drag. We are going to assume that the density of air, according to the standard pressure and temperature, is 1.19 kilograms per cubic meter. So write that down somewhere. The other thing we're going to assume is that gravity is 9.81 meters per second squared, because you're going to be dropping these at the surface of the Earth. Now, remember this little diagram that we looked at earlier? This is a comparison of the coefficient of drag for several shapes, all that have the same frontal surface area, but they have different shapes. And you can see the coefficient of drag numbers. So for a parachute design, do you want to see a higher number or a lower number for coefficient of drag? And I'll let you ponder that. G is gravitational acceleration. Oh, I just mentioned this. I'll mention it again. We're going to use 9.81 for acceleration, and that is gravity, okay? Or acceleration in a gravitational field. The theoretical impact velocity, this would be if you took your mass and it didn't have any drag and you just dropped it in free fall. What would be that velocity when it reaches the ground? You're going to need this for comparison. So without a parachute, what would be the velocity when it hits the ground? So we can calculate this more accurately than we can measure it. So the velocity at impact, or the final velocity, is going to be equal to the square root of 2 times gravity times the y displacement. So it's the square root of 2 times gravity times the y displacement. And if you would like to know more about how we got that, you can ask me to demonstrate that. It's physics, kinematics, motion in one direction. So anyway, that's the formula you need to find the theoretical velocity at impact. For mass measurements, if you have a kitchen scale, lucky you. If not, you can devise an equal arm balance. You can use rulers, and here's an example, a little cheesy one. You could even make it more simple than this, just using a stick that balances, and you could put your device on one side and put coins on the other side. So use this information from the US Mint, that a penny is 2.5 grams, a nickel is 5 grams, a dime is 2.27 grams, and a quarter is 5.67 grams. So you can use that to get a pretty good estimation of your mass of your total device. That includes the cargo and the parachute. Okay. Let's talk about the problem of area. If you cut a circle from a plastic sheet, you can find that surface area using pi r squared. But as the parachute falls, that is, in a perfect world, it would assume a hemisphere shape, and that would reduce the radius by about 30%. So let's say that we started with a 10 centimeter radius and it's falling, and that reduces to a 7 centimeter radius. That reduces the frontal surface area to roughly half. So, and I do some example calculations. The surface area of the flat sheet is 314 centimeters. The surface area of the semicircle, the hemisphere, half hemisphere, or the hemisphere is 153. So 153 divided by 314 times 100 is 48% of the original surface area. So, for the purposes of this lab, if you make your parachute out of something flat, then you're going to take that surface area and divide it by 2 when you calculate the coefficient of drag. If you have a non-flat design, you need to find the surface area of the cross-section of the bottom of the 3D shape in flight. So let's say that you went cheesy and said, I'm going to use this paper bag. So the surface area would be the size of the opening of the paper bag. Okay? So keep that in mind. So if you're using something, a flat sheet, find the surface area, divide it by 2. That's going to ballpark it. That's the easiest thing we can do for this. And that's all I have as far as introductory content for the parachute design challenge.